Your blood is older than the earth beneath your feet. The iron that runs in your veins, the calcium that strengthens your bones, and even the oxygen-binding proteins that keep you alive were not forged in the quiet laboratories of biology, but in the catastrophic deaths of ancient stars. Each atom of your body carries a history that reaches back billions of years, beyond the age of the solar system, into the furnaces of collapsed suns. Science does not use this claim as metaphor. It is literal. When physicist Carl Sagan said, "We are made of star stuff," it was not poetry. It was chemistry traced across light years of violent history. The paradox is stark. Biology, with its fragile tissues and precise mechanisms, is built from the wreckage of celestial bodies that once burned hotter than imagination can fathom. Red blood cells, endlessly cycling through your heart, carry iron atoms that were once suspended in plasma at millions of degrees. Calcium ions that allow your neurons to fire are the ashes of stellar explosions that no longer exist. Your body is a cemetery of stars, organized by DNA, structured into organs, and animated by consciousness. It is here that astronomy and physiology collapse into one another, revealing a link so vast and unsettling that it unsettles the idea of individuality itself. Blood becomes the most immediate proof. Without iron, no human breath would matter. Yet iron is not a product of Earth's geology. It cannot be produced in the hearts of small stars like our Sun. It required cataclysm, the kind of stellar death that tears apart light itself. Your survival depends on violence that unfolded long before Earth solidified into rock. Each heartbeat is a pulse of ancient astronomy. Consider this in terms of psychology. Humans instinctively search for origin stories. Ancient cultures imagined clay molded by gods, or sparks descending from the heavens. These myths may not have known stellar nucleosynthesis, but their intuition was not entirely misplaced. Modern neuroscience suggests that the human brain seeks patterns that tie existence to something larger than the self. Cognitive scientists call this agency detection, the tendency to perceive intention behind events. In the case of origin myths, perhaps this was not error, but a distorted recognition of a cosmic truth. Our matter was born from something far beyond ourselves. Physics traces this truth with precision. Astronomical spectroscopy allows scientists to decode the light of stars, revealing which elements they contain. When that light is compared to the elements in human tissue, the match is undeniable. Blood, bones, and breath carry the same spectral fingerprints as distant supernovae. In 2017, researchers at the European Southern Observatory described the iron lines in stellar spectra as identical to the iron atoms in laboratory samples. There is no separation. The atoms are continuous across time and space. This continuity unsettles psychology because it blurs the boundaries of identity. Neuroscience often frames the self as a construct of synaptic activity, bound within the skull. Yet if the self is composed of atoms older than Earth, then identity cannot be contained by biology alone. Philosophers of mind describe this as the extended self, a recognition that consciousness does not merely inhabit matter, but is inseparable from the history of that matter. Your memory may last decades, but your atoms preserve memories of stellar deaths billions of years old. They are mute witnesses carried in silence, activated only when science translates their origin. Even ritual practices show echoes of this link. Breathwork traditions, from yogic pranayama to indigenous trance breathing, place extraordinary emphasis on the act of inhalation. Oxygen enters the lungs, binds to iron in blood, and fuels neural activity. The very possibility of altered states, visions, ecstasies, feelings of dissolving into something greater, depends on a metal seated in space. Without iron, oxygen would remain useless, and no altered state could occur. In a sense, ancient breathing rituals are unconscious acknowledgments of a cosmic dependency, though they were never described in astrophysical terms. The paradox deepens when you examine mortality. Death removes the organizational structure, but the atoms remain. Bodies decay, but calcium, iron, magnesium, and carbon continue their circulation, absorbed into soil, water, or fire. In time, they may re-enter other organisms. The stars inside you are not yours alone. They are endlessly redistributed, the same way stellar remnants were scattered into the molecular clouds that later became planets. Every burial, every cremation, every dissolution of the body is a reenactment of the stellar cycle, transferring cosmic debris from one form to another. The unsettling truth is that your blood is not personal. It is borrowed. The universe has lent you atoms forged in violence to animate for a short while before reclaiming them. Each heartbeat is both intimate and impersonal, a temporary orchestration of cosmic debris. You live with the illusion of ownership, but chemistry denies permanence. The paradox remains unresolved. You are made of dead stars, yet you feel alive, singular, and conscious. The blood within you carries a silence that biology alone cannot explain. And in that silence lies a question that physiology cannot easily measure. A question written not in DNA, but in iron itself, waiting for the next layer of inquiry to unfold. Stars are engines of transformation, operating under pressures and temperatures so extreme that ordinary matter bends into new forms. At their core lies a process that physics names nuclear fusion, the merging of lighter nuclei into heavier ones, releasing immense amounts of energy in the process. This is not chemical reaction, but the reshaping of the atomic nucleus itself, a scale of change far beyond what Earth's biology can replicate. Hydrogen, the simplest and most abundant element, becomes the raw material. Within stellar cores, it fuses into helium, emitting radiation that has traveled across billions of years to reach our retinas. The warmth of sunlight, so familiar on human skin, is the surface evidence of these nuclear furnaces at work. The pathway from hydrogen to heavier elements is called stellar nucleosynthesis. Every stage represents a delicate balance between gravity pulling inward and thermal pressure pushing outward. If fusion slows, gravity dominates and the star collapses. If fusion accelerates, the star swells and destabilizes. The equilibrium is temporary. Stars live by burning their fuel, and the type of elements produced depends on their mass. Small stars like our Sun transform hydrogen into helium efficiently, but lack the gravitational compression needed to go much further. More massive stars, however, achieve pressures that drive fusion into increasingly complex stages, stacking elements one upon another, building the periodic table piece by piece. This progression has a predictable sequence. After hydrogen fuses into helium, helium itself begins to fuse into carbon and oxygen. Carbon, essential for organic molecules, is a direct product of this stellar process. Oxygen, the basis of respiration, emerges in the same nuclear crucible. In stars several times the mass of the Sun, this ladder of fusion continues upward, generating neon, magnesium, silicon, and sulfur. Each of these elements appears in the human body, not through geologic accident, but because the physics of fusion makes them inevitable once certain thresholds of pressure and temperature are surpassed. Yet fusion encounters a boundary. When nuclei attempt to form iron, the mathematics reverses. Instead of releasing energy, iron absorbs it. A star cannot sustain itself by forging iron, because the process fails to produce outward pressure. Gravity, no longer balanced, begins to collapse the stellar core inward. At that moment, an irreversible sequence begins. The star has exhausted its means of resisting its own weight. The presence of iron is not life-giving to the star. It is a signal of impending destruction. The element that later allows human blood to carry oxygen is, in its first context, a death sentence for the star that created it. The physics behind this is not abstract. It was established through decades of nuclear experiments on Earth, many of them carried out in particle accelerators and fusion chambers. Hans Bethe, awarded the Nobel Prize in Physics in 1967, mapped out the theory of stellar nucleosynthesis, showing how each stage of fusion aligns with precise nuclear reaction chains. His work confirmed that the periodic table is not random, but structured by stellar evolution. What chemistry students memorize as disconnected elements is in fact the fossil record of stars preserved in atomic form. The implications extend beyond astrophysics. To study the periodic table is to study the destiny of matter under pressure. Every element in human physiology represents a chapter in this narrative. Magnesium ions that regulate neural firing were once locked inside stellar plasma at temperatures exceeding hundreds of millions of degrees. Phosphorus atoms within DNA backbones are fragments of stellar cores that could not survive intact, except through their expulsion into space. Calcium, stabilizing skeletal structures, is a remnant of stars massive enough to fuse beyond oxygen. The entire molecular foundation of life bears the fingerprints of stellar interiors. The psychology of origin myths acquires a new dimension here. Ancient cosmologies often described creation as arising from primordial fire, whether in the Vedic concept of Agni, the Zoroastrian reverence for Atar, or the Greek image of Prometheus stealing flame from the gods. The association between fire and creation may have been intuitive recognition of a principle modern science now formalizes. Matter itself is born from fire, though on a scale far beyond human experience. Stars are furnaces whose flames shape the very atoms that become living tissue. Myth was a distorted memory of a truth humans could not yet quantify, but the resonance between cultural imagination and astrophysical process is striking. This resonance affects the brain in ways neuroscience has begun to examine. Studies in awe psychology, such as those by Dasher Keltner and colleagues, show that exposure to vast, incomprehensible scales alters neural activity in the prefrontal cortex, reducing self-focus and expanding perception of connectedness. Learning that one S-blood originates in stellar fusion is not merely an intellectual fact. It triggers a measurable psychological shift. The brain recalibrates its sense of self in response to information that exceeds ordinary boundaries. Cognitive scientists classify this as a self-transcendent experience, a state often linked to altered consciousness and even long-term changes in worldview. Yet the pathway of fusion remains incomplete without considering its instability. Fusion builds matter, but only to a threshold. Beyond that point, energy reversal forces collapse, unleashing events that scatter elements across space. Without that violent release, the products of stellar nucleosynthesis would remain locked inside stellar cores, inaccessible to biology. For human life to exist, stars must die. The quiet process of nuclear fusion inside living stars is not enough. It must be broken open, accelerated into destruction, and spread into the cosmos. That threshold introduces a different physics, one no longer governed by steady equilibrium, but by collapse and detonation, reshaping space with shock waves and light that dwarf entire galaxies. It is in that violence that the iron of blood and the calcium of bones escape confinement, traveling outward across space, waiting to be incorporated into planets not yet formed. But the mechanism of release is neither simple nor gentle, and its consequences extend beyond astronomy into the chemistry that still sustains every human body. The processes that forged atoms inside stars reach a limit. And beyond that limit, the balance shifts toward forces that biology cannot replicate, but which biology depends on in silence.
When a massive star reaches the iron threshold, the equilibrium it has maintained collapses into catastrophe. Fusion can no longer supply outward pressure, and gravity takes command, crushing the stellar core inward at astonishing speeds. In a fraction of a second, the matter inside collapses to densities rivaling atomic nuclei. Electrons are forced into protons, generating neutrons and releasing a flood of neutrinos, particles so elusive that trillions pass through every human body each second unnoticed. Yet in this moment of stellar collapse, neutrinos become agents of destruction, carrying away energy in quantities beyond anything terrestrial physics can replicate. The outer layers of the star, unable to withstand the inward rush, rebound against the incompressible neutron core. This rebound is amplified by the torrent of neutrinos pouring outward, driving a shock wave that tears the star apart. The explosion we recognize as a supernova is not a gradual flare, but a sudden release of gravitational energy converted into light, heat, and matter hurled into space. 4 days or weeks, a single supernova can shine brighter than an entire galaxy of billions of stars, illuminating the cosmos with a radiance of death. In this violence, iron, nickel, and calcium are expelled into the interstellar medium. These are the very atoms that later find residence in human blood and bone. The irony is stark. What signals collapse and suffocation for the star becomes the foundation of respiration in animals millions of years later. Iron is both the star's undoing and biology's lifeline. Without its expulsion in supernovae, oxygen could not bind to hemoglobin, and vertebrate life would be confined to a chemistry too inefficient to support complex brains. The explosion that tears apart stars lays the groundwork for cognition itself. The process has been measured in ways that connect directly to human physiology. Spectroscopic studies of supernova remnants, such as Cassiopeia A, reveal emission lines characteristic of iron and nickel. These same lines, when measured in laboratories, match precisely with the atomic signatures found in human tissues. The blood circulating through veins is, in literal terms, recycled debris of ancient stellar corpses. The connection is neither metaphorical nor poetic, but exact and testable, grounded in the physics of light and the chemistry of matter. Archaeological history even intersects with this cosmic process. In 1947, a meteorite recovered in Namibia, known as the Gibeon iron meteorite, revealed a crystalline structure called the Widmanstatten pattern. This lattice of iron and nickel forms only under conditions of extreme cooling across millions of years in space, conditions that trace back to supernova origins. When early humans discovered such meteorites, they fashioned them into tools and ornaments, unknowingly working with matter born in stellar death. Archaeologists argue that ironworking itself may have originated from such fragments, suggesting that human technological advancement is tied directly to remnants of exploded stars. Neuroscience provides a parallel dimension. The reliance of hemoglobin on iron underpins oxygen delivery to the brain. Neurons are among the most metabolically demanding cells known, consuming disproportionate amounts of oxygen relative to their mass. Cognitive states, from wakefulness to altered consciousness, depend on oxygen levels finely regulated by iron-bearing blood. Without iron in hemoglobin, the brain would suffocate under its own demands. Supernovae did not just shape the chemical environment of the cosmos, they dictated the conditions necessary for human thought, memory, and awareness to emerge. Yet the story of supernovae is not one of uniformity. Not every star ends this way. Only those with sufficient mass collapse into explosions capable of spreading heavy elements. Smaller stars fade into white dwarfs, releasing matter quietly but without forging iron. This selectivity introduces chance into cosmic history. Whether a region of the galaxy becomes enriched with iron depends on whether it hosted stars massive enough to collapse. Earth's composition is the product of stellar neighborhoods seeded by such deaths, while other regions may lack the same resources. Life's very possibility is tied to the distribution of explosions that no longer burn, their outcomes scattered unevenly across space. Psychological reflection often emerges when humans confront this kind of contingency. Theories of existential psychology, such as those by Irvin Yalom, describe anxiety as arising from awareness of chance and mortality. The recognition that life rests on arbitrary explosions billions of years ago destabilizes the idea of control. Yet at the same time, all researchers suggest that confronting such vast improbability can induce a sense of connection that reduces individual fear. This dual response, terror and transcendence, mirrors the dual role of supernovae: destruction for the stars themselves, foundation for the living beings who later emerge from their debris. The observable traces of these explosions still ripple through the galaxy. Supernova remnants, captured by X-ray telescopes like Chandra, glow with outlines of iron and silicon expanding into space. Cosmic rays, charged particles accelerated by supernova shock waves, continually strike Earth's atmosphere, sometimes interfering with electronics, but also leaving imprints in the isotopic record. Even now, fragments of ancient stellar deaths are not static. They interact with the planet and its inhabitants, embedding cosmic history into daily existence without conscious recognition. Every heartbeat, carrying oxygen through iron, echoes a process that once dismantled suns. The collapse of stellar cores created the chemical environment that human consciousness depends on. Yet the cycle of matter is not confined to supernovae alone. Other cosmic events, rarer and more extreme, contribute elements that shape both the planet and the bodies that inhabit it. Forces beyond ordinary explosions carry the story forward, adding new layers of complexity to the origins of human blood and bone. Some stellar deaths end not with outward brilliance, but with inward collapse so extreme that matter itself is rearranged. When the core of a massive star compresses beyond the resistance of electron pressure, what remains is a neutron star, an object so dense that a single teaspoon of its material would outweigh entire mountains. Under these conditions, atomic structure disintegrates, leaving only packed neutrons in configurations that ordinary physics on Earth can barely model. These remnants, though small compared to the original star, carry magnetic fields and gravitational pulls that reshape their surroundings. Occasionally, two such remnants orbit one another, spiraling closer as they lose energy through the emission of gravitational waves. Einstein's theory of general relativity predicted this century ago, describing ripples in the fabric of spacetime that propagate outward at light speed. For decades, these waves remained theoretical, undetectable against the noise of terrestrial instruments. That changed in 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, registered the tremors of colliding black holes. 2 years later, in 2017, the detection of a neutron star collision confirmed that these events do more than disturb spacetime. They are cosmic foundries for some of the heaviest elements in existence. The collision, catalogued as GW170817, released both gravitational waves and a burst of electromagnetic signals across the spectrum. Astronomers tracked its afterglow, observing signatures of freshly forged elements: gold, platinum, uranium, and rare earth metals. These were not products of supernova fusion, but of conditions even more violent. As neutron stars smashed together, their matter was ejected at relativistic speeds, and within that ejector, atomic nuclei captured neutrons at extraordinary rates. This process, known as rapid neutron capture, or the R process, produces elements beyond iron, elements that no stable star can synthesize. Gold, the archetype of human wealth, originates here. Its scarcity on Earth is not arbitrary. It is the outcome of how seldom neutron stars collide. Geological veins of gold trace their ancestry to a handful of such cosmic catastrophes scattered across billions of years. When ancient civilizations shaped gold into crowns or coins, They were working with atoms born in the collision of stellar corpses, atoms blasted across galaxies before settling into the young Earth. Platinum in medical implants, uranium fueling reactors, and lanthanides used in modern electronics share this ancestry. The technologies of wealth, power, and digital communication rest on the remnants of neutron star collisions. Psychology finds fertile ground in this recognition. Human societies have imbued gold with symbolic meaning across cultures, linking it to immortality, divinity, and incorruptibility. In Egyptian funerary rites, gold was associated with the flesh of gods, resistant to decay. In Mesoamerican traditions, it was described as the excrement of the sun, a divine residue. These associations, though framed in myth, echo the cosmic reality. Gold is incorruptible because its origin lies beyond ordinary processes. Unlike iron, it does not rust. Unlike organic matter, it does not decay. Its permanence is not just chemical but historical. It carries within its atoms the mark of neutron star collisions billions of years old. The reverence was not misplaced, though its explanation belonged to a physics still undiscovered. From a neurological perspective, the human brain responds strongly to substances associated with rarity and permanence. Neuroeconomic studies show that the ventral striatum activates more intensely in response to images of gold compared to other metals, linking value perception to deep reward circuits. This response may be partly evolutionary, tied to the practical use of rare resources, but it resonates eerily with the element's true scarcity in the universe. The brain's valuation systems align unconsciously with astrophysical rarity, rewarding the possession of matter that is, in truth, exceedingly difficult for the cosmos itself to produce. Yet the significance of neutron star collisions extends beyond cultural symbolism. These events reshape astrophysics itself, providing laboratories for physics under conditions inaccessible on Earth. In the dense matter of neutron stars, theories about quarks and gluons, the particles that compose neutrons, are tested by reality. Collisions offer data on how matter behaves at densities greater than those inside atomic nuclei, data impossible to reproduce in terrestrial accelerators. The behavior of light and gravity in these collisions also probes the fabric of spacetime itself. For human bodies to contain atoms originating here is to carry within their chemistry evidence of physical laws still under investigation. But there is a deeper consequence. The distribution of heavy elements across galaxies is patchy, dependent on where and when neutron stars collided. Not every region of the universe has equal access to gold or uranium. Planets forming in such regions inherit these differences, shaping their geology, chemistry, and possibly their capacity for life. Earth's specific inventory of elements reflects a lineage of cosmic accidents. Not just that stars exploded, but that rare collisions occurred nearby, seeding the molecular cloud that became the solar system. Biology on this planet is not merely a product of natural selection. It is also an outcome of astrophysical lottery. These collisions leave residues still detectable. Telescopes such as Hubble and the Very Large Telescope have traced kilonova afterglows, fading lights from neutron star mergers that scatter heavy elements into the void. Gamma-ray bursts, among the most energetic phenomena known, often accompany these collisions, striking detectors on Earth with signatures that reveal the magnitude of energy unleashed. The very particles expelled in these events continue their trajectories across space, occasionally embedding in meteorites or drifting into interstellar clouds that may one day birth new planetary systems. The atoms forged in these collisions, embedded now in human cells and cultural artifacts, carry silent testimony to forces that once twisted spacetime itself. Yet their journey from violent ejection into the fabric of earthly matter was neither direct nor immediate, and the path they traveled continues to complicate the question of how dead stars became the substance of blood and breath. The elements ejected from supernovae and neutron star collisions do not remain suspended indefinitely in isolation. Once expelled, they travel into the wider interstellar medium, a tenuous ocean of gas and dust that fills the spaces between stars. Though seemingly empty, this medium is a slow-moving archive of cosmic history, carrying within it atoms of every kind, drifting for millions or even billions of years before being drawn into new gravitational arrangements. The journey of these particles is shaped by forces invisible to the naked eye: magnetic fields threading galaxies, shock waves from subsequent stellar deaths, and the quiet pull of gravity working across unimaginable distances. What emerges from this long dispersal are clouds of dust and gas, regions of enriched matter where the debris of countless stars gathers. These nebulae, illuminated by ultraviolet radiation from nearby stars, appear as luminous shapes through telescopes, yet their beauty conceals violent origins. Each wisp of glowing gas contains calcium, iron, carbon, and silicon atoms born in explosions long extinguished. In time, the turbulence within such clouds creates regions of density, where matter clumps together under its own gravity, compressing into colder, darker forms. These molecular clouds become incubators, holding the seeds of future stars and planets, and by extension, the chemistry of life itself. Dust particles within these clouds act as scaffolding for chemical complexity. Coated with ices of water, methane, and ammonia, they provide surfaces where molecules assemble, sometimes forming precursors to organic compounds. Laboratory simulations, such as those conducted at NASA's Ames Research Center, have demonstrated how ultraviolet light striking such dust grains can generate amino acids and nuclear base-like molecules. These are not yet life, but they are the architecture from which living systems can later be constructed. The interstellar journey of stardust is not passive drift but active preparation, setting chemical possibilities into place long before planets condense. Astronomy traces these processes through spectroscopy, capturing the faint fingerprints of molecules in distant nebulae. Observations of the Orion Nebula and the Eagle Nebula, among others, reveal the presence of complex hydrocarbons, alcohols, and even sugars. Each detection is a record of chemistry occurring in regions that may one day collapse into new solar systems. The very compounds later found in meteorites that strike Earth, glycine, ribose, and other organic molecules, can be matched to the chemistry of interstellar dust. In this sense, the journey of stellar debris is not random scattering, but a continuous circulation of potential, connecting the deaths of stars with the birth of biochemistry. The brain's perception of cosmic scale often struggles with this slowness. Cognitive psychology identifies a limitation known as temporal myopia, the difficulty humans face in conceiving of processes beyond familiar time spans. 1,000,000 years, let alone 1 billion, exceeds the intuitive capacity of memory and imagination. Yet these durations are routine for interstellar matter. A calcium atom expelled from a supernova may drift for half the age of the galaxy before being incorporated into a forming planet. To grasp this timescale requires abstract reasoning, a capacity that neuroscientists associate with the prefrontal cortex, the same region involved in counterfactual thinking and long-term planning. Contemplating cosmic timescales is itself a cognitive exercise that stretches the architecture of human thought. Cultural practices have often symbolized journeys of this kind through myths of wandering or exile. In Greek cosmology, the story of Persephone describes a descent and return, while in Mesopotamian myth, Inanna's journey through the underworld reflects cycles of death and renewal. These narratives, though not about astrophysics, echo the underlying truth that matter disperses, travels, and reforms in new shapes. Just as mythic figures return transformed from their wanderings, so too do atoms expelled by dead stars reappear in transformed states, as mineral veins, as ocean salts, as the hemoglobin carrying oxygen through bloodstreams. The correspondence between myth and physics lies in the pattern of dispersal and return, recognized intuitively long before science measured it. The path of stardust is also influenced by phenomena of extraordinary subtlety. Galactic winds, driven by clusters of supernovae, sweep material into intergalactic space. Magnetic fields thread this dust into filaments, guiding its motion across thousands of light years. Cosmic rays, high-energy particles accelerated by shock waves, strike dust grains, altering their chemical bonds and sometimes shattering them into smaller fragments. Each interaction is part of a continuum that prevents matter from settling, keeping the interstellar medium in constant circulation. By the time any atom becomes part of a planetary system, it has undergone countless transformations, carrying a silent history of collisions, absorptions, and displacements. Meteorites provide tangible evidence of this journey. Carbonaceous chondrites, some of the oldest rocks in the solar system, preserve isotopic anomalies that match those found in distant stars. These inclusions, known as pre-solar grains, are microscopic crystals of silicon carbide and graphite that predate the Sun itself. When scientists analyze them, they find isotopic ratios impossible to explain by solar processes, confirming their origin in supernovae and neutron star collisions. Holding such a grain in a laboratory is holding matter that wandered through space for eons before being trapped in the forming solar nebula. It is physical proof that human bodies contain not just atoms forged in stars, but atoms that survived entire galactic journeys before reaching Earth. The psychological resonance of this knowledge lies in its capacity to destabilize the boundaries of self. If atoms of the body once drifted alone through interstellar clouds, their presence in blood or bone does not erase that history. Consciousness may regard them as part of identity, but their timeline extends far beyond individual existence. This realization can evoke both disorientation and awe, producing cognitive states akin to those recorded in mystical experiences. William James, in The Varieties of Religious Experience, described awe as a dissolution of personal boundaries into something larger. Modern neuroscience records similar responses when subjects confront cosmic imagery, noting alterations in the default mode network associated with self-referential thought. The journey of stardust is not only a physical process, but also a trigger for psychological states that blur the distinction between individual and cosmos. Yet the path of atoms drifting through nebulae does not end with indefinite wandering. Gravity exerts a quiet persistence, gathering matter back into dense knots that will collapse into stars and planets. The enriched debris, having traveled across vast distances, becomes seed material for new worlds. But the way this material is drawn together, shaped, and organized into solid bodies requires another transformation, one that brings the cosmic journey into direct contact with the formation of the very ground beneath human feet. The collapse of enriched molecular clouds initiates a sequence that transforms dispersed stardust into structured systems. Under gravity's pull, matter accumulates into a rotating disk, a protoplanetary nebula, where temperature and density vary with distance from the central condensation. At the core of this disk, a new star ignites, surrounded by rings of gas and dust that serve as raw material for planetary construction. The early solar system emerged from such a configuration, drawing together remnants of ancient stellar explosions into organized layers of rock, metal, and volatile compounds. The differentiation of matter within this disk was not uniform. Closer to the young sun, heat drove off lighter gases, leaving behind silicates, metals, and minerals that coalesced into rocky planets. Farther out, colder regions preserved ices of water, ammonia, and methane, accumulating into gas giants and their moons. This division between inner and outer worlds shaped the trajectory of planetary chemistry. Earth's iron-rich core, its silicate mantle, and its volatile oceans are consequences of where the planet formed within this temperature gradient. Each feature reflects not only gravitational physics, but the chemical inheritance of earlier stellar deaths. Iron played a decisive role in planetary evolution. During Earth's early molten state, heavy elements sank toward the center, forming a dense metallic core, while lighter silicates floated outward to create the mantle and crust. This separation, known as planetary differentiation, established the conditions for a magnetic field, as liquid iron in the outer core generated currents that shielded the surface from solar radiation. Without this protection, The fragile molecules that later assembled into life would have been stripped away by high-energy particles. The same iron that in human blood enables oxygen transport first served as the dynamo preserving Earth's atmosphere. Its role in biology was preceded by its role in planetary survival. The delivery of volatiles, including water, added another layer to Earth's complexity. Evidence from isotopic analysis of ancient minerals, such as zircons dated to over 4 billion years, indicates that liquid water existed early in Earth's history. Yet the source of this water remains debated. Some models suggest it arrived via comets or hydrated asteroids, carrying ices formed in the cold outer regions of the solar system. Others argue that water was incorporated directly into the forming planet through binding with silicate minerals. In either scenario, hydrogen and oxygen, elements forged in stars, were reassembled into oceans that later hosted the first biological activity. The seas themselves are monuments to stellar chemistry, held together by bonds first written in nuclear reactions light-years away. Dust grains within the protoplanetary disk also acted as crucibles for organic chemistry. Analyses of meteorites, such as the Murchison meteorite that fell in Australia in 1969, reveal amino acids and nuclear-based precursors embedded within their structures. These compounds survived entry through Earth's atmosphere and retain isotopic ratios indicating extraterrestrial origin. The implication is that planetary formation incorporated not only inorganic elements but prebiotic molecules assembled in interstellar space. The stage for life was set by materials older than the Sun itself, preserved through the chaotic birth of planets and delivered intact to young surfaces. The geologic layering of Earth encodes this heritage. Elements such as silicon, magnesium, and oxygen dominate the crust, while trace elements, zinc, copper, molybdenum, are dispersed in or deposits, concentrated by processes of volcanism and tectonics. Each of these trace elements has essential biological roles: zinc in enzyme function, copper in neural signaling, molybdenum in nitrogen fixation. Their availability on the surface depends on geophysical processes that redistributed matter during planetary cooling. Biology exploits this arrangement, but it did not create it. The scaffold of life is contingent on mineral distributions set by planetary physics, which in turn are inherited from stellar explosions. The psychological response to this chain of causality often borders on disorientation. To recognize that the capacity for thought depends on tectonic processes reshaping stardust challenges the narrative of human centrality. Neuroscience describes this reaction as cognitive disequilibrium, a state in which established mental frameworks are destabilized by new information. Experiments show that such destabilization can provoke both anxiety and heightened curiosity, often leading to deeper exploration. In confronting the planetary consequences of stellar matter, the human mind oscillates between awe at the vastness of connection and unease at the fragility of its foundations. The transition from nebula dust to a living planet also carries implications for time perception. Planetary accretion spanned tens of millions of years, a duration incomprehensible to ordinary cognition. Cognitive scientists studying deep time describe how humans struggle to visualize processes beyond a few centuries, let alone geological epochs. Yet every stone, every ocean current, and every trace element within the body carries the mark of these spans. To exist on Earth is to inhabit a structure that condensed over timescales the mind cannot grasp, yet whose consequences permeate every aspect of physiology. Evidence of Earth's early history remains embedded in ancient rocks, but those rocks also reveal instability. The early planet endured constant bombardment by asteroids, intense volcanic activity, and fluctuations in climate driven by a young, volatile sunday. Through this turbulence, the chemical groundwork for life persisted, sustained by the very elements seeded by stellar death. The durability of these elements ensured that, despite planetary upheaval, the building blocks of biology remained present and available. The stage was set not only for matter to persist, but for it to begin interacting in ways that transcended mineral chemistry. Yet the reorganization of stardust into a planet did not by itself create life. It prepared the ground, concentrating the essential elements into environments where new forms of complexity could emerge. The iron in Earth's core, the oxygen in its atmosphere, the carbon in its mantle, and the nitrogen in its sky formed the framework, but the transformation into living systems required another leap. Within the oceans and minerals of the young Earth, the atoms once scattered across interstellar space began to assemble into molecules that carried energy, stored information, and moved toward structures capable of replication. The same debris that once drifted as cosmic dust now gathered into a chemistry that pressed against the threshold of biology. The chemistry of Earth's early oceans carried within it the potential written into stellar debris, but life could not emerge without harnessing the properties of specific elements. Iron became central to this transition. Its unique electron structure allows it to shift between oxidation states, moving easily between Fe superscript 2 and Fe superscript 3, a property that makes it an ideal carrier of electrons in redox reactions. Long before animals relied on hemoglobin, primitive microorganisms exploited this versatility, using iron to catalyze the transfer of energy in metabolic pathways. Rocks from ancient banded iron formations, dating back more than 2.5 billion years, preserve evidence of these processes, recording how early life began drawing power from reactions made possible only by stellar iron. The eventual incorporation of iron into hemoglobin represented not a new invention but an extension of this deep relationship. Hemoglobin's structure places an iron atom at the center of a porphyrin ring, allowing oxygen to bind reversibly. This chemical arrangement is delicate. Oxygen attaches strongly enough to be carried, but weakly enough to be released in tissues where it is needed. The efficiency of this system allowed animals to grow larger, to move with speed, and to sustain the high metabolic rates required by complex nervous systems. The iron atom at the center of hemoglobin is not incidental. It is the hinge on which vertebrate physiology turns. Without it, no mammalian brain could sustain its oxygen demands. The brain's dependence on oxygen is extreme. Though it accounts for only about 2% of body mass, it consumes around 20% of the body's oxygen intake. This disproportion reveals how tightly cognition is linked to respiratory chemistry. Neurons require constant oxidative metabolism to maintain ion gradients, propagate action potentials, and recycle neurotransmitters. If oxygen supply falters, even briefly, consciousness fails. The vulnerability of human thought to interruptions in ion-mediated oxygen delivery underscores the depth of our reliance on stellar chemistry. What was once plasma in a supernova became the indispensable medium of memory, language, and imagination. This link between iron and consciousness also shapes psychological states. Practices that manipulate breathing, whether yogic pranayama, Tibetan tummo, or modern techniques like holotropic breathwork, alter the availability of oxygen in blood. By adjusting the rhythm and depth of respiration, individuals can shift blood chemistry, reducing or elevating oxygen and carbon dioxide levels, thereby influencing neural excitability. Reports of altered states, visions, dissolution of ego boundaries, sensations of unity, are mediated through fluctuations in oxygen delivery made possible by hemoglobin. Ancient practitioners may not have known the molecular basis, but their experiences were inseparable from the iron atoms in their blood, atoms inherited from long-dead stars. Iron also shaped planetary environments in ways that directly influenced biology. Before oxygen accumulated in Earth's atmosphere, vast quantities were absorbed by dissolved iron in oceans, precipitating out as iron oxides that layered into the banded formations seen today. This great oxidation event, occurring around 2.4 billion years ago, marked a turning point. Once the ocean's iron was saturated, oxygen began to accumulate in the atmosphere, transforming the planet's chemistry. That transition created both crisis and opportunity. Anaerobic organisms perished in toxic conditions, while others adapted to use oxygen as a more efficient energy source. Human respiration, reliant on iron-bearing hemoglobin, is a distant inheritance of this planetary transformation. Without the interplay between stellar iron and atmospheric oxygen, complex life could not have stabilized. From a neurological perspective, oxygenation levels modulate not only survival but cognition. Functional MRI studies rely on this principle, tracking changes in blood oxygenation as proxies for neural activity. Hemoglobin, shifting between oxygenated and deoxygenated states, provides the signal that allows researchers to visualize thought processes in real time. The very technology used to peer into the brain is enabled by the same iron chemistry that sustains the brain itself. It is a feedback loop. The element born in stellar collapse carries oxygen to neurons, and its spectral properties allow scientists to observe the activity those neurons produce. Cultural traditions have long mirrored this connection between breath, blood, and vitality. Ancient Egyptians associated the heart with both thought and life force, believing it to be the seat of intelligence and morality. While anatomically misplaced, the intuition linked circulation with consciousness. In Chinese medicine, qi was described as a vital breath or energy flowing through the body, sustaining health. These metaphors, though constructed without molecular knowledge, resonate with modern physiology. Iron-driven oxygen transport is quite literally the flow of life, determining the boundaries between awareness and unconsciousness. Yet iron's role in biology carries risks as well as advantages. Its capacity to shift oxidation states makes it prone to generating free radicals when unregulated, damaging cells and accelerating aging processes. Neurodegenerative disorders such as Parkinson's and Alzheimer's have been linked to dysregulated iron accumulation in the brain. Here again, the duality of iron emerges. It is both essential and hazardous, a legacy of stellar processes that gave rise to life but also impose vulnerabilities. The same atom that sustains consciousness can, when imbalanced, undermine it. The precariousness of this balance underscores the tension inherent in humanity's elemental heritage. The iron that binds oxygen to blood is indispensable, yet it operates on a narrow edge between sufficiency and toxicity. The fragility of this equilibrium mirrors the larger fragility of life's reliance on rare cosmic events. If iron had not been produced in sufficient abundance by supernovae, or if Earth had formed in a region of space devoid of such debris, no vertebrate physiology could have evolved. The very existence of conscious organisms depends on a chain of improbable conditions converging across stellar, planetary, and biological scales. The circulation of iron through blood is not merely a chemical mechanism, but a continuation of processes set in motion long before the planet formed. Every breath depends on an element that once destabilized stars. Every thought relies on atoms forged in their deaths. Yet blood alone does not tell the whole story of stellar heritage within the body. Other elements, equally violent in origin, inhabit the skeleton, the muscles, and the nerves, extending the reach of cosmic ancestry beyond respiration into every structure that sustains human life. Bones, nerves, and muscles, though distinct in function, all bear the imprint of stellar debris woven into their composition. Calcium, magnesium, sodium, and potassium, elements forged in the fusion stages of massive stars and expelled into space by their violent deaths, now orchestrate the physiology of living organisms with quiet precision. Where iron anchors respiration, these other elements establish the frameworks, rhythms, and signals that hold bodies together and enable their actions. Without them, the architecture of skeletons would collapse, electrical activity in neurons would fail, and the muscular contractions that sustain movement and circulation would cease. Calcium stands foremost in this structure. Its abundance in bone is not incidental, but essential to vertebrate stability. Hydroxyapatite, the crystalline form of calcium phosphate, forms the mineral matrix that hardens bones and teeth, transforming soft tissue frameworks into durable supports. The rigidity of this mineral scaffolding allowed organisms to evolve beyond the limitations of fragile cartilage, enabling terrestrial life and the development of complex body plans. Archaeological analysis of fossilized skeletons reveals the universality of calcium's role across deep evolutionary time, its presence recording an unbroken chain of reliance on an element born in the core of dying stars. Yet calcium is not confined to bones. In cells, its movement across membranes serves as a signaling mechanism that coordinates processes ranging from muscle contraction to gene expression. In neurons, the influx of calcium triggers the release of neurotransmitters at synaptic junctions, allowing communication between cells in the brain. Without these ion fluxes, thought itself would stall. The same atom that mineralizes bones also pulses invisibly in neural circuits, orchestrating the cascade of signals that constitute memory, perception, and decision-making. Its dual role, structural and electrical, demonstrates how one element can underlie both the solidity of the skeleton and the fluidity of consciousness. Magnesium operates in quieter domains, but no less crucially. As a cofactor for more than 300 enzymatic reactions, it stabilizes ATP, the molecule that stores and transfers energy within cells. Every contraction of muscle fibers, every repair of DNA, every transmission of nerve impulses depends on magnesium's stabilizing influence. The evolutionary choice of magnesium, rather than another metal, stems from its abundance in ancient oceans and its versatile chemistry. Its isotopic signatures, traced in marine sediments, reveal a continuous cycle between seawater, geology, and biology, a circulation echoing the broader cycle of elements across the cosmos. Sodium and potassium extend the network of stellar inheritance into the domain of electrical excitability. The resting potential of neurons, the voltage difference that primes them for firing, is established by gradients of sodium and potassium ions across cellular membranes. Action potentials, the fundamental pulses of neural activity, are generated by the rapid flow of these ions through specialized channels. The brain's ability to coordinate movement, store memory, and generate language depends on the ebb and flow of elements that once drifted as fragments of stellar explosions. Even the simplest reflex, a muscle twitch in response to a stimulus, is a reenactment of cosmic history, translated into the language of ions. The vulnerability of this system illustrates the precarious balance on which life depends. A disruption in calcium metabolism leads to brittle bones or uncontrolled neural firing, while deficiencies in magnesium contribute to arrhythmias and muscular weakness. Imbalances in sodium and potassium can induce paralysis or seizures. Modern medicine, with its reliance on electrolyte regulation, is in effect a practice of managing the distribution of stellar elements within the body. Intravenous saline solutions, dietary supplementation, and pharmaceutical interventions all operate on the principle that health requires precise orchestration of atoms delivered long ago by stellar deaths. Cultures across history have intuited the significance of these substances. Ancient physicians prescribed mineral salts for ailments, while mythologies frequently associated bones with permanence and continuity of the self. In many traditions, bones were preserved or venerated as relics, carrying symbolic weight as vessels of identity. The chemical truth embedded in these practices is that bones do not merely endure after death. They preserve the calcium of ancient stars, locked in crystalline form, awaiting return to the geological cycle. To hold a fragment of bone is to hold cosmic matter stabilized into living architecture. Neuroscience adds another dimension to this recognition. Studies on long-term potentiation, the mechanism underlying memory formation, demonstrate that calcium influx into neurons is critical for strengthening synaptic connections. The persistence of memory, the ability to carry forward experiences across time, is dependent on ions that trace their origin to stellar fusion. Every recollection, from mundane detail to profound insight, rests on atomic pathways that connect directly to the cosmos. When calcium channels falter, as in certain neurodegenerative disorders, memory disintegrates, revealing the fragility of this dependence. The psychological implications of recognizing bones, nerves, and muscles as cosmic structures extend into states of altered consciousness. Practices such as fasting, rhythmic chanting, or sensory deprivation shift electrolyte balances and neural signaling, sometimes producing visions or dissociative states. Anthropological studies suggest that such practices were often interpreted as contact with the divine or entry into other realms. In biological terms, they reflect the reorganization of elemental flows within the body. The perception of transcendence emerges from the rearrangement of calcium and sodium ions across membranes, a process at once ordinary and extraordinary. Yet these elements did not gather into bodies by accident. Their presence in human physiology is a consequence of Earth's inheritance from earlier stellar generations, and their persistence in biology depends on ongoing planetary cycles that recycle them through soil, water, and atmosphere. Each meal, each breath, replenishes a chemistry rooted in explosions that predate the solar system. The skeleton grows, the muscles contract, the neurons fire, all by borrowing matter from a reservoir that is both terrestrial and cosmic. The continuity of these processes reveals an unsettling truth. The very atoms that compose living structures are transient occupants, exchanged continually with the environment. The calcium in bones cycles from food to bloodstream to skeleton and back again, just as sodium and potassium shift between diet, cells, and excretion. The body is not a static possession of cosmic matter, but a temporary configuration through which these elements flow. And within that flow lies the deeper question of how cultures, myths, and sciences interpret the human condition when confronted with the knowledge that even identity rests on borrowed atoms, still carrying the memory of stars. Across cultures and centuries, humans have attempted to explain their origin through symbolic stories, weaving together soil, sky, and divine intervention. These myths, though conceived without astrophysics, often mirror truths that science would later uncover. The Babylonian Enuma Elish describes humanity formed from the mingling of earth and divine essence. In Greek mythology, Prometheus shapes humans from clay, animated by stolen fire. In the Hebrew Genesis, Adam's name is drawn from Adamah, the ground, linking humanity to dust. These narratives, though culturally distinct, converge on the intuition that human life is inseparable from the material world and the heavens above it. The parallel with cosmic chemistry is striking. The clay of myth can be read as silicon and oxygen minerals, abundant in Earth's crust. The divine fire resembles the fusion processes that give rise to light and energy in stars. Even the notion of breath as spirit, present in traditions from Ruach in Hebrew to Pneuma in Greek, resonates with oxygen's central role in physiology. Without the atoms scattered by supernovae and neutron star collisions, there would be no clay to mold, no fire to animate, no breath to sustain. Mythmakers intuited a connection that science later traced to nuclear physics. Anthropology suggests that such myths are not arbitrary. Cognitive scientists argue that humans construct cosmologies as extensions of pattern recognition, the same faculty that allows survival in uncertain environments. Agency detection, hyperactive in the human brain, perceives intention in natural forces, transforming floods, storms, or fertility into acts of gods. Yet in the myths of human origin, this same faculty aligned with a deeper truth. Life is inseparable from material processes beyond human scale. While framed in symbolic terms, these stories foreshadowed the astrophysical insight that the body is built from elements older than the earth itself. The Vedic hymns of India describe Purusha, the cosmic being sacrificed so that his body becomes the world. His mind the moon, his breath the wind, his bones the mountains. Though poetic, the metaphor aligns with the scientific recognition that cosmic matter structures every aspect of life and environment. In Norse mythology, Ymir, the primordial giant, is slain and his body transformed into the earth, sky, and sea. These mythic dismemberments resemble in symbolic form the scattering of stellar bodies into fragments that later condense into planets and living beings. The resonance is not literal, but the intuition is consistent. Existence is assembled from the remains of something larger, something that perished to make way for life. Modern neuroscience provides insight into why such myths feel compelling. Functional imaging studies of narrative comprehension show activation in the default mode network, associated with self-referential thought, and in limbic structures tied to emotion. Stories that place human identity within a larger cosmic order generate both meaning and affective resonance. This combination of cognitive coherence and emotional weight may explain the persistence of origin myths across cultures. They serve not only to explain material origins, but to integrate individuals into a framework that transcends personal mortality. Science does not replace this impulse. It reframes it. The recognition that hemoglobin carries iron forged in stars, or that bones contain calcium expelled by supernovae, supplies a cosmology of its own. Unlike myth, it rests on spectroscopic data, nuclear theory, and isotopic analysis. Yet the psychological effect is similar. Exposure to scientific accounts of cosmic origin has been shown to evoke awe, a state linked to reduced self-focus and heightened prosocial behavior. Experiments conducted by psychologists such as Paul Piff demonstrate that awe-inducing stimuli, whether vast landscapes or astronomical imagery, increase generosity and ethical decision-making. The scientific recognition of stellar ancestry may thus shape not only knowledge but behavior, mirroring the social functions once served by myth. Even language itself carries traces of these intuitions. Words like inspiration derive from notions of breath, illumination from light, vitality from life force. Each encodes metaphorical associations between human existence and natural phenomena tied to cosmic processes. The metaphors endure because they map onto biological realities. Breath depends on oxygen, light sustains circadian rhythms, and vitality rests on the flow of electrons through cellular respiration, all processes anchored in stellar chemistry. Linguistic patterns, shaped by generations without access to astrophysics, nonetheless preserved resonances that align with later scientific understanding. The persistence of these intuitions across time suggests that human cognition may be predisposed to recognize connection with larger scales of reality, even if only dimly. Psychologists describe this as transcendent cognition, mental states oriented toward concepts beyond immediate survival. Such cognition often arises in altered states, whether through ritual, meditation, or pharmacological agents, where boundaries between self and world appear porous. The recognition that matter itself flows between stars and bodies provides a material grounding for such experiences, connecting subjective perception with physical continuity. Yet the recognition of cosmic origin introduces tensions as well. The same myths that affirm humanity's connection to the heavens also grapple with mortality, portraying death as return to dust or dissolution into cosmic order. In the Epic of Gilgamesh, the hero confronts the inevitability of death, told that humans are destined to perish while gods endure. In scientific terms, this tension persists. The atoms of the body may be ancient, but the organization of those atoms into consciousness is temporary. The contrast between permanence of matter and impermanence of self continues to shape human psychology, fueling both anxiety and awe. The fusion of cultural intuition and scientific evidence does not eliminate mystery. It intensifies it, grounding existential questions in measurable processes while expanding their scale. The recognition that human myths anticipated aspects of stellar chemistry raises further questions about perception, cognition, and the ways in which cultures encode knowledge before they can articulate it scientifically. The boundary between imagination and reality becomes porous, and within that porousness lies an unfinished inquiry that presses against both science and meaning. Every beat of the human heart is a mechanical rhythm, yet its origin is inseparable from atomic histories written in ancient stars. The contraction of cardiac muscle depends on calcium ions moving in and out of cells, sodium and potassium gradients shifting across membranes, and, above all, the steady delivery of oxygen bound to iron in hemoglobin. Each pulse is the convergence of stellar chemistry and biological architecture, maintaining circulation not just of blood but of the universe's oldest elements through living tissue. The centrality of iron to this process extends beyond transportation of oxygen. It anchors the very structure of the proteins that perform it. Hemoglobin's iron atom forms a reversible bond with oxygen, strong enough to prevent suffocation in the lungs, weak enough to release oxygen where tissues consume it. This balance allows for continuous movement of molecules through the vascular network, a flow measured not in isolated breaths, but in years of unbroken exchange. Life exists in the interval between oxygen's binding and release, a cycle that repeats billions of times within each individual across a lifetime. The relationship between circulation and consciousness is absolute. Cerebral neurons begin to fail within seconds of oxygen deprivation, a vulnerability demonstrated in clinical observations of hypoxia. Studies of pilots exposed to high altitudes without supplemental oxygen describe cognitive impairment, progressing rapidly from confusion to unconsciousness. The brain's dependence on oxygen is so immediate that even minor fluctuations in blood flow can alter awareness. Fainting, strokes, and ischemic episodes are biological reminders of the fragility of this system, each event an interruption of the link between stellar iron and thought. Yet the reliance on stellar matter is not only functional but also experiential. Practices such as meditation and controlled breathing subtly manipulate oxygen intake, influencing blood chemistry and altering neural rhythms. Neuroimaging studies of advanced meditators show decreased activity in the default mode network, associated with self-referential thought, alongside increased coherence in attention-related circuits. These shifts depend on the precise regulation of oxygen supply through hemoglobin. The altered states described as transcendence or dissolution of the ego are inseparable from the iron atoms embedded in every red blood cell. What feels like escape from the material body is, paradoxically, mediated by it. The vulnerability of circulation also shapes cultural understandings of life and death. Ancient rituals often placed emphasis on the heart as the center of vitality. In Egyptian funerary practice, the heart was weighed against the feather of Ma'at, symbolizing truth and balance. This metaphor resonates with physiology. The heart maintains balance between life and its cessation through unceasing motion. Yet science reveals that the rhythm depends not on mysticism but on stellar chemistry, with each contraction supported by ions and elements scattered into the galaxy long before Earth existed. Even the electrical signals that initiate each heartbeat are expressions of cosmic matter. The sinoatrial node, the heart's natural pacemaker, generates rhythmic impulses through ion flows of sodium, potassium, and calcium. Electrocardiograms, used clinically to trace these impulses, are indirect measurements of elemental motion at the atomic level. To see the peaks and troughs of an ECG is to witness stellar debris moving within a body, translated into the pattern of a heartbeat. What appears as medical data is, at another scale, a living record of the cosmos sustaining itself through physiology. This perspective complicates the distinction between self and environment. The oxygen delivered to the brain in each breath was once part of a planetary atmosphere shaped by geological and biological cycles. The iron carrying it was expelled from stars that collapsed billions of years ago. The calcium coordinating contraction was forged in stellar cores and later concentrated through planetary processes. The body does not produce these elements. It borrows them, orchestrates them temporarily, and returns them. The illusion of separation is sustained by organization, but the material continuity reaches far beyond individual identity. The psychological effects of contemplating this continuity are not uniform. For some, the awareness that each breath depends on ancient explosions provokes feelings of insignificance, aligning with existential theories that describe anxiety as arising from recognition of mortality and contingency. For others, the same awareness evokes awe, producing a sense of connection with scales of existence that extend beyond the personal. Experimental psychology confirms this duality. Awe can reduce self-focus while enhancing perceived meaning. Whether disorienting or elevating, the recognition ties the intimate rhythm of blood to forces that operated long before life arose. Even in death, circulation does not end so much as it transforms. The organized movement of blood ceases, but the elements remain, dispersing into soil or ash, beginning new journeys of redistribution. Calcium leaches into sediment, iron oxidizes into rust, carbon returns to atmospheric cycles. Burial and cremation are not merely cultural rituals. They are chemical processes returning stellar matter to broader circulation. The atoms of an individual become part of ecosystems, geological layers, or even future organisms. The continuity of matter persists, even as its configuration shifts beyond recognition. This recognition raises questions not only of science but of perception. If identity is rooted in configurations of borrowed atoms, then the persistence of those atoms blurs the boundary between existence and dissolution. Consciousness may not continue once circulation stops, but the matter that sustained it does, re-entering cycles that may again converge into structures capable of awareness. The blood that sustains life is temporary, but the atoms within it remain, carrying their silent memory of stars into futures not yet formed.